Good afternoon, everybody. Let's start our work, and what it will be lecture on medical and biological physics on optics. First of all, we'll consider optics basics, and after that it will be more close for your future specialty. It will be optics principles of biological objects investigation. So let's start, please. What it will be, the goals: quantification of optical radiation matter effect as substantiations of optical method choice for biological objects research. What does this mean? You must to argue, it will be better to say to prove that just this optical method is the best for that biological object research. This is the goal for us to investigate. Objectives: optics, parameters, nomenclature, and basic laws reviews, physics aspects of optical radiation matter effects, review of optics research methods, and instrumentation principles. And our plan is this: introduction, physics models of optical radiation matter effect, physics principles of biomedical research by optical instrumentation, summary and bibliography. Okay, let's start from the introduction. The investigation of the human condition using light can hardly be avoided. All patients are seen by their doctors, and external appearances are used in many diagnoses. Internal observations could obviously bring much additional information. The opportunities are as simple as the mouth. All that is required here is to open wide and say "ah." Specially focused beams enable internal viewing of the eye and the ear. In most cases, a tube and endoscope has to be inserted into the orifice to see inside the body. So this is just that opportunities for you to widen the range, the spectrum of the diagnosis of the patients. Look, we start from the optics parameters nomenclature and the basic laws review. Optics actually is physics section on optical radiation phenomenon. What is this? Occurrence, propagation in space, and matter effect. This is just the problems for the optics to consider. Optics is of two sub-branches, in accordance with two physics models that used to describe optical radiation propagation and matter effect. First branch is geometrical optics. It uses the physics model of optical radiation as light ray beam. It is just the physics model. And what is the advantage of this model? It is very simple. Simplicity for what? To understand the matter effect of optical radiation. The next, wave optics. Physics model for this is electromagnetic wave. Advantage: color is described naturally in terms of wavelength. This is quantification of the radiation. We determine the wavelengths instead of that to say it is blue color, it is green color. No, wave optics gives the instrument to quantify the description of optical radiation. This required in order to explain the interaction of light with material objects of sizes comparable or smaller than a wavelength of light. And finally, one more, particle model, but it is not just for the optics. required in order to explain the interaction of light with the individual atoms. At the atomic level, it becomes apparent that a beam of light has a certain graininess to it. And what is actually optical radiation? It is the range of the wavelengths of the electromagnetic waves, it will be better to say exactly, electromagnetic waves of particular certain wavelength range. What is that range? It is from 10 to the power 2 up to 10 to the power 4 nanometer. Optical radiation is subdivided into ultraviolet range, visible, and infrared. You can see what are wavelengths diapasons for these three optical radiation ranges. And more detailed, let's discuss or let's get the review about optical radiation generation production. Actually, it is particular range of electromagnetic waves. Electromagnetic waves are emitted by elementary particles, in particular electrons, at their oscillations. You can see this is illustrated by that means charge. It might be electron or any other pointed charge, for example, as it is shown here, single charge. What does it do? It oscillates up and down, and this produces that as electromagnetic energy. Actually, what is this? It is the process of the energy transformation. Mechanical energy of the moving charge is transformed into another kind of energy, electromagnetic energy. And we talk about the generation of electromagnetic energy by moving, oscillating electric charge. But actually, one more time, let me repeat, it is the transformation, one kind of energy, mechanical energy, into another kind of energy, electromagnetic energy. One more situation might be to generate electromagnetic energy. For example, look here, it is the atom, and it is collided by the fast-moving particle. What does this mean? Particle possesses kinetic energy of its motion. And one more time, this energy is given to the atom. We said this energy is absorbed by atom. And what is the result? One more time, this energy is transformed into the energy of the electron into the atom, and electron is delivered with the energy and goes to the higher excitable orbit. But it is not stable position of the electron, and it comes back to its original state, and the portion of electromagnetic energy that is named here a light photon is generated, is produced. A collision with a moving particle excites the atom. This causes an electron to jump to the higher energy level. The electron falls back to its original energy level, releasing the extra energy in form of a light photon. Look, this portion is assumed to be as the particle, because it is the local of amount portion of energy, and in some particular cases it behaves itself as the particle. So when collision with another atom or a chemical electron excites an atom, an electron in the atom absorbs the energy, boosting it up to the higher level shell. The boost is short-lived and the electron immediately falls back down to the lower level, emitting its extra energy in the form of an electromagnetic energy. So you can see one more time, we discuss the processes of the energy transformations in one form into another form. Okay, and let's look inside that electromagnetic energy and recognize its structure, I may say so, or nature, as you wish. So electromagnetic energy actually is carried by electric and magnetic fields propagating through this space. When we talk about this oscillating electric charge up and down, what should be said else? Not only the motion should be mentioned, but also we should say about the electric field that is developed, that is produced into its vicinity of this charge. When it starts to move, the electric field becomes to be not static, but it becomes to be alternating electric field. Immediately after the first instant of its change produces the magnetic field, and this magnetic field follows in its change the change of electric field. So that is why it becomes to be such community, one electric field producing the magnetic field. In turn, that change in magnetic field is producing electric field, and this combination of the electric and magnetic fields that are linked in a continuous mutual transformation, this is just represent electromagnetic field phenomenon. If the motion of the charge is of oscillatory nature, look, this is just the distinguishing feature of the physics. When we talk about oscillation, please, what is this? It is mechanical motion. And how this may be represented? By this analytical equation, showing how this change takes place into the space. We take the y-axis, coordinate axis, and to say about motion, we can write down this analytical equation of the change of this coordinate with time. That's all. No comments is required now. The oscillation, the motion following this change of the coordinate into the space, up and down, for example. And you can see this oscillation is of this circular frequency. It will be the same circular frequency for the electric field and magnetic field to oscillate. What does this mean, the oscillation of the electric field and magnetic field? One more time, it is shown directly. The vector representing electric field changes its magnitude and direction into the space with time. And this change at a particular instant of time is represented by this graph. Same. What is the oscillation of the magnetic field? It is the oscillation of the vector representing magnetic field into the space with time. One more time, you can see that this vector changes its direction and magnitude with time, and this is expressed concretely how this happens with time. At any instant of time that is of interest, we can know the position of the vector into the space, and we can know its magnitude, orientation, position. This combination is propagating in the direction that is perpendicular to the planes at which vector of magnetic field and vector of electric field are oscillating. That is, the planes where within which these vectors are changing their magnitudes and orientations. So, and you can see this combination, this continuous mutual transformation of the energy from electric to magnetic field is going through the space with this velocity, if we will consider the vacuum or the air at normal condition. It is just electromagnetic energy that is propagating into the space. Nothing, meaning the substance, is carried, and by this wave the only energy is going through this space, and this phenomenon is called the wave. We met already the analog of this phenomenon. It was the sound, it was mechanical wave. So when we talk that there is no noticeable motion of the substance. Substance is required for the mechanical wave, but not for this case. The only energy is propagating into the space, and this phenomenon of energy propagation not to be carried by substance is named the wave process. W-A-V-E. Wave. Okay, let's go further. And the electromagnetic waves propagate in matter with the ultimate speed, and you can see this is a velocity of propagation of electromagnetic waves is determined, depends on the substance, on the matter the electromagnetic wave crosses, and these parameters that are matter, dielectric and magnetic permeabilities determine the velocity of electromagnetic wave propagation. So these epsilon 0 and mu 0, electric and magnetic constant respectively, and these constant magnitudes you can see here. And what should be said else as the quantitative characteristic of electromagnetic wave? First of all, the velocity of the propagation. By the way, look, let's come back to this. And when we talk about wave, we should classify this wave as to be longitudinal or transverse. And you can see that the vectors of electric and magnetic fields are vibrating, oscillating at the planes that are perpendicular to the direction of the wave propagation. So this determines the electromagnetic waves as transverse waves. It is the kind of transverse waves. So, and wavelengths. When we talk about wavelengths, we can notice two parameters that are, I can say, natural for the wave. What is the one parameter? It is the time period of the one completed oscillation of the vector of electric field, or that is same the time period of one completed oscillation of the magnetic field vector. And this is just the wave period. The next, how many times are the completed oscillations within 1 second? It is just the frequency of the wave, in our case, electromagnetic wave. What are oscillating? The electric and magnetic field vectors representing them. And we talk now about the completed cycle, one completed oscillation of these vectors per unit time, and this is just the frequency. So, and the period, if we know frequency, we can know as well. It is 1 second. We divide this by the number of the oscillation per how many are within the 1 second, and we obtain the time of one completed oscillation. So, and wavelengths. What is the wavelengths? It is the distance of the propagation of electromagnetic energy within the time equals to one time period. So, this is the velocity of electromagnetic wave propagation into the matter. We time this by a period and obtain the wavelengths. It is the distance for the energy to travel within time equals to the one time period of the oscillation of the electric or magnetic field vector. And this is the maximum speed, velocity of electromagnetic waves propagation. It is in vacuum, equals to around 3 times 10 to the power 8 meter per second. And this, you can see, is inversely proportional to these parameters of the matter. This reveals that this is the maximum velocity, and in all other substances, in all other kinds of matter, the electromagnetic wave propagation is less. So, and these are quantitative characteristics: wavelengths, period, and frequency. So the speed of propagation, velocity of propagation, and one more, what is at the core of electromagnetic wave? At the core is electromagnetic energy, so that is why we have to quantify just this. Electromagnetic wave energy. Electromagnetic waves carry energy as they travel through empty space or when they travel through the matter. So, nevertheless, they carry energy. So that is why we can say about how much energy crosses the surface of the, for example, flat plate, for example, something like this, that is perpendicular to the direction of the propagation, and we want to recognize how much energy is crossing this surface per unit time. And this becomes the rate of energy transport. When we divide this by the area of the surface, we obtain the rate of energy transport per unit area. So, and this is of particular direction. So that is why this amount of energy should be considered as the vector. It is Poynting vector, and the magnitude of this vector, Poynting vector, or the energy density or intensity equals to this product. The rate of energy transport, look, is perpendicular to the both electric and magnetic field in the and in the direction of propagation of the wave. So the energy, the rate of energy transport. The Poynting vector magnitude, that is electromagnetic wave intensity, equals to this. We discussed already this as intensity. You might remember this from the acoustic. We say about the sound intensity. One more time, it is not different. It is the energy crossing the unit of the surface per unit time. That's all. And average intensity for a plane wave equals to this. So quantification of the electromagnetic wave phenomena. So the next, let's go further. What is this? When we talk about the propagation into the space, you might remember we noticed that velocity of the electromagnetic wave is the greatest into the vacuum. In all other matter, in all other substances, the velocity is less. So that is why to determine this, to quantify this, we should say about this parameter, let me show you this parameter as index of refraction. Index of refraction. It is defined as the speed of light in a vacuum divided by the speed of light in the medium. Index of refraction. So that is why it becomes absolutely clear what do we mean when we talk about different substances. We talk about different indexes of refraction. So, and one more time, it is the quantification to make more clear discussion. So we talk the substance is of this index of refraction and this substance is of this index of refraction. So it becomes absolutely clear that these two are different. So meaning the velocities of propagation into these two substances, these are different because we discuss now just the effect of electromagnetic radiation. The matter, this is that parameter revealing this effect. Matter changes the velocity of propagation of electromagnetic wave. Okay, so let's come back and let's start from this simplest as I said already, model of light. We deal now with geometrical optics basics, and you can see here the illustration of this model of light as light beam, light ray. It is the arrow line with arrow. The arrow shows just the direction of the propagation electromagnetic energy, and when we don't need to recognize how light interacts, affects the matter at atomic structural level, and when we are only of interest of propagation of light through the medium, we can ignore this nature of light, of electromagnetic energy as electromagnetic energy, and we can stop at this idea. Okay, electromagnetic energy is propagating, nothing is more of our interest. So that is why we show this direction of the propagation and stop with this. In geometrical optics, we consider the simple case. The propagation of light is straight lines if media are homogeneous and transparent. Interfaces are not uneven, so these interfaces are smooth. That gives specular, regular reflections. So that is why we ignore or we don't deal with the surfaces, interfaces, with the noticeable irregularities on them. So, in geometrical optics, the analysis of the behavior of light is carried out with physics model, light rays. So, and this is shown here how this may be illustrated, this model. And the first geometrical optics law is the law of reflection. I understand and it is clear for me that this is new for you, but let me refresh your minds. Only this. What is the purpose, what is the aim for this? To show you, after I refresh your minds, how this physics, how this theory works, particularly in medicine, how this is at the base of the medical instrumentation. So is the law of reflection. It is the first geometrical optics law. The angle of reflection equals the angle of incidence. But what is said by that means? What is said by that means? That light, optical, electromagnetic radiation falling the smooth surface, flat smooth surface, changes its direction of the propagation. It is just the meaning, the physics of the first geometrical optics law. So you can see the incident ray is the straight is shown as straight line. It falls the smooth flat surface separating two homogeneous optically uniform media, and after this it changes its direction of propagation. These are too many words to be said, but we can quantify this situation. How? Let's put the perpendicular at the point of the incidence and let's measure the angle of the incidence. It is the angle between the perpendicular and the line showing the direction of the propagation of electromagnetic energy. So, and this is the angle. So, if we talk about the direction, we say what is the magnitude of this angle, and it becomes absolutely clear what is the direction of the propagation of the incident ray. When we talk about the change of this direction, one more time, we show the new direction of the propagation of the reflected ray, and this new direction we quantify, we make certain by angle of reflection that is measured between the line showing the new direction of propagation of the light beam and the perpendicular. So, and this is just absolutely strong objective statement about quantitative statement about how light changes its direction of propagation after interaction with a flat, smooth surface separating two homogeneous, optically uniform substances media. So the second geometrical optics law is the law of refraction. It is Snell's law, you know. So what happens? If the contacting with the first medium, the next adjacent medium is uniform and transparent as well, electromagnetic energy partly crosses the surface separating these two and propagates into the second adjacent medium. One more time, it changes the direction of propagation. Why does it happen? Why does it happen? Because of the change of the velocity of the propagation. Medium changes the velocity of electromagnetic energy propagation, and this is revealed by the change of the light beam direction. One more time, what is the quantitative measure of this new direction? The angle of refraction that is measured. We continue perpendicular crossing the surface separating these two media and go into the second media, and this becomes one more perpendicular for the refracted ray, and the angle between the refracted ray and this perpendicular is just the quantitative measure of the change of the direction of the propagation. Snell's law, and you can see that it is not random change of the direction of the propagation. This is determined by these as indexes of refraction of two media. These indexes determine the angle of refraction at the particular angle of the incidence. And look how this may be interpreted, may be utilized. The internal reflection. Internal reflection. It is the case actually of refraction, at proper incident angle. So, when light is incident upon a medium of less index of refraction, so this index of refraction Nt is less than this Ni. The ray is bent away from the normal. You can see away from the normal. So, the exit angle is greater than the incident angle. The angle of refraction is greater than angle of incidence. Such reflection is commonly called internal reflection. The exit angle will then approach to 90 degrees for some critical incident angle, and for incident angles greater than the critical angle, there will be total internal reflection. So, and you can see threshold condition for total internal reflection. It is just this critical angle of the incidence. And for this, the final light beam doesn't go into the second medium, but it goes along the surface separating these two media. Total internal reflection. No light goes into the second transparent optically uniform media, but all energy comes back into the first medium. And look how this works. It might be determined So you can see this is the glass fiber. So, and the incident angle is proper, and it is called the half angle of the fiber, since it represents the half field of view that can be transmitted. And if this will be the incident angle of the external light going into this glass fiber, into this glass tube, the critical angle of incidence on the glass fiber surface will be reached, provided, and the light starts to go through this fiber to be internally reflected, and this may provide the propagation of light for long distances. So the fact that look, what should be noticed here, there is no loss of energy when we talk about total internal reflection. All energy is reflected and returns to this fiber. So that is why this is the condition that is satisfied to propagate the light energy, electromagnetic energy for long distances. So once the light is introduced into the fiber at this proper angle, into the fiber with an angle within the confines of the numerical aperture of the fiber, it will continue to reflect almost losslessly of the walls of the fiber, and thus can travel long distances in the fiber, as I said already. So, and you can see independently on curvature this total internal reflection is maintained and light goes through this fiber. And this is just at the core of the fiber optics instrumentation, at the core of the fiber optics instrumentation. Fiber optics, you can see this glass fiber, and light goes into this fiber and up to the end, and this is just the exit for the light, but at the lateral surfaces you can't see the light going outside. So, and without change of the intensity, this light may be delivered to the distal places that is of interest to view, to visualized, to be visualized, to be investigated. Fiber optics imaging uses the fact that the light striking the end of an individual fiber will be transmitted to the other end of the fiber. Each fiber acts as the light pipe, transmitting the light from that part of the image along the fiber. Even if pipe curves gradually, light will travel its entire length and arrive unattenuated after many reflections. A bundle of these fibers produces the fiber optic light guide. If the arrangement of the fibers in the bundle is kept constant, then the transmitted light forms a mosaic image of the light which struck the end of the bundle. So, and look, when we talk about the flat surfaces separating the two optically uniform substances, we talk about the change of the direction of the propagation of the electromagnetic energy, and same will be when the surface will be curved of a particular radius of curvature, as it is illustrated here. You can see this curved surface of spherical curved surface, and the radius of this curvature of this spherical surface is marked here by symbol R. So nevertheless, when light goes, for example, to be reflected from the object point O, it goes and strikes that curved surface. After this, it goes into the second transparent medium at a different angle to the normal that is drawn at the point of the incident. So, and this means the change of the direction of the propagation, and this gives the such special kind of change of the direction of the propagation by curved surfaces gives the opportunity to obtain images of the objects of amplified linear sizes, to magnify the object's images by that surfaces. So, and there is an object O, and a ray of light from the object O is incident on the spherical surface of the curvature center C and radius R. Since the ray is moving from a rarer medium to a denser medium, lens for example, so this is shown, and there is no any word required to say about this difference between the media. So the ray ON bends toward the normal NC, and image is formed at the point I. At the point I. One more time, it is not random point, it is determined, absolutely certain point that is determined by that equation. Actually, what is this? It is this equation showing that if you place the object at the distance u from this curved surface of the transparent substance medium, you obtain the image of this object at the distance v after light crosses this denser medium. So this is absolutely strongly determined. So, and u is the object distance from a pole of a spherical surface, v is the image distance from a pole of the spherical surface. So, and look, let's come back to that we start from. What is this? It is the nature, it is just that showing one more time the nature of electromagnetic wave. It is the energy actually carried by electric and magnetic fields. So, and this energy so is carried by that fields, and we say about the oscillations of the vectors of electric and magnetic fields. And when we talk about the optical radiation matter effect, we should make our choice between these two vectors. Look into this substance, we meet when we look inside them, we meet the atoms, and when we go deeper into the atoms, we can find electrons that are charges, and atoms nuclei that carry protons, positive charges. So when we talk about the substance, we have to talk about very complicated, huge complicated electric field combinations, elementary electric fields combinations, and it is understandable that this electric field resultant of the substance is influenced, can be influenced by electric field, first of all by electric field of electromagnetic wave. So that is why when we talk about electromagnetic wave, we first of all discuss the behavior of the electric field vector. So, and just now we talk about this here. Look, it is the natural, common light produced by the lamp, for example, and these are the directions, the planes of the all possible directions and planes where at which the electric field vectors of this light may oscillate at. But it may be made choice of the only one plane of the oscillations of the electric field vectors, and this may be done by the crystal, that is named as polarizer. Not all electromagnetic waves will go through the polarizer. Polarizer will make its choice. It separates from other waves the only waves with the only one plane of electric field vector oscillations, and this light becomes to be polarized. Natural light emitted by a bulb of intensity, and it has electric and magnetic fields vibrations in all directions. When ordinary light is incident normally on one face of a thin crystal with its faces cut parallel to its crystallography axis, the vibrations in the emergent light are confined to the plane containing the direction of propagation and the axis of the crystal. Such a beam of light is said to be plane polarized. The plane of polarization is that plane in which electric and magnetic fields vibrations occur. So one more time, let me pay your attention. The electric elementary fields into the substance influence the external electromagnetic electric field and make this electromagnetic wave electric field vibrations ordered. So what does this mean? All vectors of the electric field are now of the only one plane of their oscillations. This light being passed through a polarizer has the half of the initial intensity. It is understandable. The only part of the light is chosen by the polarizer. The intensity of light passed through the analyzer is found to be of less intensity, one more time, if the angle between the axis of polarizer and analyzer is not zero but of particular magnitude. You can see the optical axis, main optical axis of the second polarizer, that is analyzer, is at angle to the main optical axis of the polarizer. So that is why when light to be polarized crosses the analyzer, this analyzer reorientates the plane of polarization of polarized light. It changes its orientation into the space. It rotates that plane of polarization, and this decreases the intensity of light crossing the analyzer. It is the Malus law. Malus law, experimental data showing analytically what happens. So, and look, one more time, when we talk about the electromagnetic radiation affect the matter, this is caused by interaction between electric fields of electromagnetic wave and local elementary electric fields of the atoms of the matter. So, and one more time, electromagnetic energy is carried. Atoms can absorb this energy. This is the extra energy for the atoms, and this means that this energy of electromagnetic radiation is not lost, but it is transformed into the extra energy of the substance. Atoms energy. So that is why intensity after electromagnetic radiation crosses the substance decreases, and this decrease depends on the substance and depends on the electromagnetic radiation. A little bit later, it will be next time at the next lecture, we will talk about the very specific absorption by the atoms of the electromagnetic energy. Because look, when we talk about the absorption of energy, this means that atom becomes to be excited, electrons inside the atom goes to the higher energy level, but these energy levels are not random. But these are of particular heights, that energy excited levels, and this structure of that excited energy levels are very specific and different for different elements, for different kinds of atoms. So that is why we should say, we should pay our attention that the absorption depends on the substance, and there is preferential energy that is absorbed at the greatest extent by the substance. So, and this is because of the energy levels structure of that element atoms. So, and if we talk about that electromagnetic wave of that preferential wavelengths, This law, Lambert-Beer law, is showing how intensity is changing when radiation crosses this particular substance of that molar absorption coefficient, of this concentration, and of this thickness of the layer of that substance. One more time we talk about the electromagnetic radiation that is of the most absorbance by this substance. The molar absorption coefficient varies with the wavelengths of the radiation. The ratio between the absorbed light intensity and the incident light intensity is defined as absorptance. It is absorptance. The ratio between the transmitted intensity and the incident light intensity is defined as transmittance. And the decimal logarithm of the ratio between the incident light intensity and the past light intensity is called absorbance. So, and this molar extinction coefficient is equal to this. So, consequently, if you will measure the absorbance, you can just this equation shows that the absorbance that can be measured gives you information about the concentration of the substance, particularly in the solution or into other transparent matter. Okay, and one more time. Let's come back to the polarization of the light that crosses polarizer and analyzer, but this is implemented into the optical instrumentation for biomedical research. It is just polarimetry. There are some substances, organic, particularly amino acids, proteins, sugars, that may be considered as the optically active. They behave themselves as the polarizer, so, and at the same time, when the polarized light goes through the solution of that optically active substance, they work as analyzers. They rotate the plane of polarized light polarization. So that is why, by that means, these optically active substances may be revealed, may be recognized, meaning their presence. So, and in some cases, in medicine, in biology, it is of interest. For example, it is just very important information about the presence of the glucose into the blood plasma. So this instrumentation, polarimetry, is just for this, particularly for this. When a beam of plain polarized light is passed through crystals and solutions, it is found that the plane of polarization is rotated through an angle. This phenomenon or property of rotating the plane of polarization is known as rotatory polarization or optical activity, as I said. Substances like sugar crystals, sugar solutions, solutions of proteins, nucleic acids are optically active. For dilute solutions, the angle of rotation in radians is of this magnitude. One more time, you can see it is angle of rotation of plane polarization of polarized light. So, and this is the specific rotation defined as rotation produced by a liquid or solution that is under investigation of length 1 meter and concentration of 1 kilogram per meter cubed. It is just the identification of that optically active substance. This is constant for any substance that is under investigation. And this is just the concentration into the solution, and this is the length of the tube cuvette where solution is placed. And you can see this principal optical diagram of the polarimetry optical instrumentation. One more time, the ordinary light is focused. It is of all possible planes and directions of vibrations of electric field vector. It goes through the polarizer, and after that it becomes polarized. The only one plane of the vibration of electric field is chosen, and all vectors are oscillating just at that plane. It is the plane of polarization. After that, it is the polarimeter tube with the sample that is under investigation. It is of particular length, L. And you can see this optically active substance rotates, reorientated, changes the orientation of the plane of the polarization. And one more time, analyzer that initially was at parallel position to the polarizer can't allow to cross all these changed polarized light, and the viewer at the eyepiece will see the less intense light. So polarimeter used to measure the optical rotation of molecules in the solution. One more time, you can see this diagram. And what is the idea? Idea is just this. Okay, we agree that after crossing the tube with the optically active substance, the plane of polarization of light is changed, and less light, Malus law works. And less light goes to the eyepiece, and the idea is to measure just this angle of rotation and use it to calculate the concentration. So analyzer is a rotable polarizer. This lens is rotated until no light goes through the second lens. Lens means analyzer. The angle is then measured to determine the optical rotation, for example, as in this case of the amino acid. So that is why the handle is used to cross the polarizer and analyzer and to measure that angle of rotation done by the optically active material into the polarimeter tube. So, and after that, concentration is calculated. Polarimeters therefore measure the angle through which the ray of polarized light is diverted. Depending on the design of the device, the second filter is then rotated manually or automatically until no light falls on the detector. So that is why, look, what I didn't mention. It might be two cases. What are these two cases? You place the polarizer and analyzer at the positions with the parallel main optical axis. And this means that without sample that is investigated, the light that is polarized after it crosses the polarizer will go through the analyzer without change of intensity. And at the eyepiece it will be the bright field. But it might be a different situation. You put this analyzer at the position when the analyzer main optical axis is perpendicular to the main optical axis of the polarizer. So that is why these crossed positions of the polarizer and analyzer doesn't allow light to go through the analyzer, and at the eyepiece you'll see the dark field. And this is just the case illustrated here. So after light will go through the tube with the sample, this light is of different plane of the polarization because of rotation by the sample optically active substances. And we will see not dark field at the eyepiece, but it will be more or less light. So that is why you take handle and rotate analyzer and rotate it to obtain the dark field. And this rotation compensate rotation of the light done by the optically active substance. This angle is determined here and used to calculate the concentration of optically active substance. So polarimetry will provide information about the molecular structure. Are there optically active molecules, substances, or there are no that substance, the concentration of the substance, and sometimes information about the solvent used. The optical activity is also influenced by temperature. Should be remembered the wavelengths of the light and the lengths of the optical path. It is understandable. The longer the path of the light through an optically active substance, the larger the angle of rotation. These variables may be used to control the sensitivity of the instrument. Polarimetry, polarization of the light. And look, one more interaction of the electromagnetic radiation with the substances. This is the absorption. Light or electromagnetic energy goes through the substance, and atoms are excited, but the possible energy levels are strongly determined by that or another chemical element. So you can see here, first stage is to obtain this graph and determine the wavelengths of the maximum absorbance for element that is under investigation. And what is investigated? One more time, the presence and the concentration of the transparent solutions that are colored. This is just the colorimetry. Involves the measurement of the amount of light absorbed by a colored sample. The molar absorption coefficient is a proportionality constant between the absorbance. This is just measured decimal logarithm of the ratio of the intensities. And concentration for a given path length. A plot of absorbance versus wavelengths is called the absorption spectrum of the substance, and it is the first stage of the colorimetry. Colorimetric analysis are normally carried out at the wavelengths of an absorption maximum, since the molar absorption coefficient is least sensitive to changes in wavelengths near the maximum. And this is the diagram of that colorimeter. Photocolorimeter. So white light goes through the filter, becomes to be colored, becomes to be of particular wavelengths of that, to calibrate, first of all, to calibrate this and to make a choice of these special wavelengths. After that, this goes through the tube with a sample, and this is the light sensitive cell and matter, and this data of the absorbance is shown here. So, and what is that method? It is the first of all the calibration of the colorimeter. You use several samples of known concentrations, these standards, and you calibrate absorbance, investigate the magnitude of the absorbance versus concentration, and after that, when you need to investigate the solution with unknown concentration, you do the simple thing. You take that solution, measure its absorbance at that particular wavelength of maximum absorption, and from the graph you determine the concentration of unknown solution. Calibrated method of calibration is used to determine the concentration. You don't need each time to use this formula. It is done already by this device, by this instrument. At a particular wavelength, Lambert-Beer law can be used to relate absorbance and concentration for a given path. So, and this is reconstructed by that device. What should be mentioned else? Look here, this absorbance measurement is of two stages. First of all, you put on the way of the light, the cuvette with the solvent only. After that, you look and see the absorbance just of the solvent, and you put mechanically by handle, you put you make the reading equals to 0, and by that means you subtract the absorption by the solvent. After you put on the way of the light the solution of the substance of interest, the reading will correspond to the absorbance of that substance only, and this will be without the absorbance of the solvent. So, and this becomes more correct investigation of the concentration. Colorimetry, photocolorimetry. And one more time, let's come back to the fiber optic imaging and look how this works for medical purposes. It is the fiber optic endoscope. This is the fiber optic endoscope. You can see if the bundle is to be used to transmit image of the inside of the body, then attention has to be paid to a number of factors. There will be a loss of intensity due to absorption and scattering by the glass, which will depend on the length of the fiber. So production methods are now such that there is very little loss over the length required for observing part of the body. Maximum length about 1 meter. So endoscopy is basically a tube for looking into the body. The person credited with its invention is German cosmologist in the late 19th century. The instrument that is shown here is the long flexible shaft containing the fibers, is usually made of helical steel bent inside the steel mesh to prevent the glass fiber from damage whilst permitting the wide range of movements required. So you can see this, and this shaft is about 10 millimeter in diameter and up to 2 meter long, depending on the application. At the far or distal end is the bending section, which is fully controllable from the operator's end to carry out the motion and minor operations. So, and look, endoscopy is the insertion of a long thin tube directly into the body to observe an internal organ or tissue in detail. What is the task? The glass fiber bundle brings the light inside the human body. The light reflects from the structures, and this reflected light brings the images of that structures. It can also be used to carry out other tasks, including imaging and minor surgery. Endoscopes are minimally invasive and can be inserted into the openings of the body, such as mouth or anus. There are many different kinds of endoscopy, and you can see that organs that might be under investigation of the endoscope. So, and this is invaluable information about the condition of the organs. And finally, several words about that instrument that you know and that you practice, experience already. It is the microscope. Microscope is the technical field of using microscopes to view samples and objects that are not within resolution range of the normal eye. The object under study is placed just beyond the focal point of the objective. Its image is real and inverted, and it is much larger than the object. The linear magnification is just this, and it is typically around 50. This magnified image then serves as the object for the ocular, which acts as a simple magnifier and provides the one more time amplified image, meaning the magnified, it will be better to say, the image for the viewing at this physiological distance. And the total resultant magnification of the microscope equals to this. So the magnification might be from 10 up to 1000 times or more, but you should take in account not only that opportunity as to magnify the linear size of the object under investigation, but also the invaluable information about the object may bring the details that you can observe. So that is why resolution should be taken in account. When the separation between 2 points in a microscope specimen is comparable to the wavelengths of the light, we would expect diffraction effects to be important. The minimum separation that can be resolved by a microscope is determined by this equation. So, and the resolution of any light microscope is about 250 nanometer. And look, this is the minimum distance. And if you will take another not light microscope, ultraviolet, for example, you decreases the wavelengths, and this microscope ultraviolet will be of greater resolution. So, and one more thing, if you put between the objective and specimen, if it is possible, the medium with the greater than air index of reflection, immersion, for example, fluid, liquid, you decrease this distance, and the resolution is increased by this by that means. But you can't change the instrumentation configuration, you can't change this, so that is why when you make your choice of the optical instrumentation, you should remember what is the task: to magnify the size or to observe the details of that specimen microscope. So, and look how the modern microscopes may look like. So you can use the display, not eyepiece, to recognize what is under microscope, and this is more comfortable manner to investigate specimen. So, in summary, basic principle of optical method is the implementation of optical radiation to examine objects' conditions. Optical instrumentations quantify optical radiation parameters that objectively specify objects' conditions. So, we use electromagnetic energy. We investigate how substance, matter, changes the parameters of electromagnetic energy, and this is made, the information is brought in quantitative style, so that is why this becomes to be absolutely objective, independent on investigation, invaluable information about state, about condition of the specimen or patient that is under investigation. So please, we finish, and this is just a bibliography. This Physics in Biology and Medicine, 4th edition, Davidovich. You can use to add that information we discussed, I represented to you just now. This will be supported by your tutorial practice, so that is why we continue to deal with this at the tutorials. Thank you for attention. We finish. Time is over. Have a good day.